Around the mid-1800s, discrete line spectra were observed when a high voltage was applied to a low-pressure gas. In the second half of the 19th century, scientists expended great efforts in measuring the wavelength of line spectra of different elements. They discovered that each element produces a specific set of spectrum lines, kind of like fingerprints for elements. Scientists could use the spectrum produced by a gas to tell which elements are involved. For example, in 1862, Swedish scientist Anders Enström found hydrogen spectrum lines in solar spectrum, which led to his discovery of hydrogen's presence in the sun's atmosphere. Then in 1885, Swiss mathematician Johann Balmer used trial and error methods to develop this simple formula that gives wavelengths that match Enström's wavelength measurements for hydrogen spectrum lines. By the way, you do not need to memorize this formula. Now let's go back to the atom models. In 1913, our understanding of the hydrogen atom took a giant leap when Niels Bohr introduced his model for hydrogen atom that allowed him to derive Balmer's formula. Bohr's model is based on Rutherford's planetary model, but Bohr felt that he needed to incorporate the newly developed ideas of quantum physics. He made 4 postulates. 1. Electrons in hydrogen atoms move in circular orbits about their nuclei. 2. An electron in orbit has a definite amount of energy without giving off EM radiation, so the orbits can be stable. 3. EM radiation is emitted only when an electron transitions from higher to lower energy level. EM radiation is absorbed only when an electron transitions from lower to higher energy level. 4. Only certain circular orbits are allowed. Bohr made his quantum assumption to match experimental data, Balmer's formula. I'm not going to derive it here, but this is the equation for the energy of an electron at the nth level in a hydrogen atom. En equals to negative 13.6 EVs divided by n squared. And n is 1, 2, 3, that kind of whole number, and n is a quantum number or energy level. This is an energy level diagram for the Bohr model of hydrogen. If I plug in n equals to 1, I get negative 13.6 EVs. If I plug in n equals to 2, I get negative 3.4 EVs, n equals to 3, negative 1.5 EVs, and so on and so forth. When I plug in n approaches to infinity, I get E equals to 0. That means the electron is no longer bound by the atom. As you can see, the energy between different energy levels has the biggest gap between n equals to 1 and n equals to 2, and then 2 and 3, and 3 and 4, and so on and so forth. And for large n's, the energy is very, very close together. The n equals to 1 is also called the ground state. The ground state has the lowest energy. As we go up, the energy gets higher and higher, and then to 0 for n approaches to infinity. The 13.6 eV is the binding energy or ionization energy for n equals to 1, the ground state, which means if an electron is at the ground level, we will need to provide 13.6 EVs to bring that electron to E equals to 0, so that electron can be freed and leave the atom, and therefore the atom becomes ionized. That's why it's called ionization energy. What do you think is the ionization energy if the electron is at the n equals to 2 state? That will be 3.4 EVs, because that's how much we need to move the electron from negative 3.4 EV to 0, to move from n equals to 2 to n approaches to infinity. A hydrogen atom can give off EM radiation when its electron transitions from an upper energy state to a lower one, like these. the emitted photon would have energy hf that equals to the energy of the upper level minus the energy of the lower level. If the lower energy state of this transition is n equals to 1, which means the transition goes from 2 to 1, 3 to 1, 4 to 1, etc., then the transitions would involve the most amount of energy because this gap involves the most energy. Then those photons will be in the UV range, and that's called the Lyman series. If the lower energy level is n equals to 2, that means the transition would go from 3 to 2, 4 to 2, 5 to 2, etc. And this range of energy gives us visible light, and that's the Balmer series. Because they're in the visible light range, that's why the Balmer series were the ones that were observed first. It's worth noting that when Bohr made his quantum assumption, he only aimed at matching the empirical data. Then in 1923, de Broglie explained Bohr's quantum assumption using standing electron waves in circular orbits. If you remember, when a string oscillates in loops, in standing waves, we have resonance and energy can build up, and energy does not get lost easily. Now if we loop the string around in circles, resonance would happen if the string oscillates in even number of loops, which means n equals to 1, the ground state, has 2 loops. N equals to 2 has 4 loops. N equals to 3, 6 loops. And if you remember, the length of one loop is always half the wavelength. That means n equals to 1, 2 loops, that means 1 wavelength. So for n equals to 1, in the circumference 2 pi r, there is 1 wavelength. For n equals to 2, the circumference should equal to 2 wavelengths. That's why we have 2 pi times r equals to the energy level number times wavelength. So n equals to 3, 6 loops, means the 2 pi r equals to 3 times the wavelength. And it turns out that this matches Bohr's quantum assumption exactly. So the wave-particle duality is essential for this successful atom model.